Now we're going to look at first-order linear ODEs. The standard form for such an equation is y prime plus py equals q. So let's take a look at this guy. All right, so in the homogeneous case, we have y prime plus py equals 0 because it's homogeneous. And then this is going to be a separable equation because we can just solve for y prime as being minus py, and then we have y prime over y is equal to p, and all the y's are on the left and all the x's are on the right, and so the, minus p, well, okay, that's a mess, minus p. But if we have the non-homogeneous case, y prime plus py equals q for q, not the zero function, then this guy is not separable. And there's not really any way to see that other than that if you try and separate it, you'll see that it fails. Okay, so let's look at how to solve such an equation. Well, actually, you know what? Let's back up. Before we try and solve such an equation, what I would like you to do is this. So thinking about y as a function of x, differentiate for me the expression y of x times e to the integral of p of x dx. Okay, so just go ahead and symbolically integrate that. Pause the video for a moment and give it a shot. Okay, so if you're going to differentiate this, you notice first that it is a product. So we're going to need product rule. So that tells you you're going to have one term where the derivative goes on the y. So y prime times, and then the exponential completely unaltered, plus y times, and now we've got the derivative of the exponential function, which is going to be just the exponential function exactly as it is, times, by chain rule, the derivative of the exponent, which, since it's an integral, so this is d dx integral of p, so that's going to simplify. So I've still got my y prime e to the integral of p, and then y times, and this expression right here, well, the derivative of an integral is just the integrand. So it's going to be py e to the integral p dx. And so I can factor out that expression, and I have y prime plus py times e to the integral p dx. And so the reason why I wanted to do that is because this expression here in the parentheses, that is exactly what we have on the left side of our differential equation here. And so so this gives an idea. What we're going to do is we're going to multiply y prime plus py equals q by the integrating factor, which is this crazy looking exponential. So e to the integral of the coefficient of y. Okay, why would we do that? Well, then what happens is on the left, we're going to get y prime plus py e to the integral of p. And on the right, we're going to get q times e to the integral of p. But then we just saw that the this part here on the left is actually this derivative right here. So I can make that substitution on the left-hand side, and this becomes d dx y times integral e to the p equals integral e to the p times q. And so now I can integrate both sides of this equation here. So slap an integral on each side. And on the left side, what's going to happen is it's just going to cancel the integral and the derivative. And so I'll have y e to the integral p. And then on the right side, I'll have, well, some big ugly integral. So integral e to the integral pq. But then look, now I just have to move this exponential over to the other side, and I can solve for y equals, and then I've got all the other junk over here. So this formula that I've written is sort of awful, but it gives you the idea for a method which is fairly straightforward. Okay, and so to solve, so here's how you solve a linear first order differential equation. So step one, make sure that you've got the ODE written in standard form. And this is just so that you can see exactly what your function p is supposed to be. Okay, and then step two, compute the integrating factor. And so in a given example, this might require some amount of work. So so what you're going to do is you're going to determine the coefficient of y here and then integrate it. So you take the integral of that p, and then you exponentiate the entire thing. And that'll be your integrating factor. Then you multiply this along or across both sides of the differential equation. And then what you should do is you should verify. So this is a handy check that you've done the arithmetic correctly and that you've set things up right. Verify that the left side is the derivative of mu, your integrating factor, times y. So this should always happen. That was the first computation that we did, and that's why we set things up that way. So this one is a very good double check. If you don't get that working out, then that means that there was an error in your arithmetic and you should go back and fix it now. Then you can integrate both sides. And on the left, you'll have y mu. And on the right, you'll have whatever that stinking integral was. So this is, whoops. And then you solve for y just by dividing the mu over to the other side. Whoops. So we'll have y equals 1 over mu integral mu q dx plus c over mu. There you go. So that's it. Okay, so now if you were watching closely, you might have noticed that I was playing a little fast and loose with the constants of integration. So specifically, if we come back up here to step 2, where we compute the integrating factor, you might think, oh, well, there should have been a plus c up there in the exponent. But look at what would happen if there were such a thing. Okay, so that would make this our integrating factor c e to the integral of p, right? So then if we multiply across both sides of the differential equation, then we would have c e to the minus p times y prime plus py equals c e to the integral p times q. And the very first thing that I would do then is just cancel that constant from both sides. And so why even have it there in the first place?